calculating the test statistic F with equal sample sizes N. The next slide below can be very helpful in understanding the methods of ANOVA. In a table, we're going to compare dataset A to dataset B to see that dataset A is the same as dataset B with this notable exception. Sample 1 values each differ by 10. If the datasets all have the same sample size, as in n is equal to 4 for the table, the following calculations aren't too difficult. So let's take a look here. Okay, here's dataset A, and then here's dataset B. For sample 1, we have 7366. Sample 2, we have 6558. Sample 3, we have 4767. Now for dataset B, what we've done for sample 1 is we added 10 to each of these values. So sample 1 is 17, 13, 16, and 16. And then sample 2 remains the same at 6, 5, 5, 8. Sample 3, we have 4, 7, 6, 7. Okay, so the first thing we're going to do is find the sample size. So the sample size for N1 is 4, sample 2 is 4, sample 3 is 4. And then for dataset B, sample 1 is 4, sample 2 is 4, and sample 3 is 4. Okay, and then if we find the mean using StatCrunch, whatever the case may be, the mean of those four numbers of sample 1 is 5.5. The mean of sample 2 is 6.0. The mean of sample 3 is 6.0. In dataset B, the mean of sample 1 is 15.5. The mean of sample 2, again, is 6.0 in dataset B, and the mean of sample 3 is 6.0. Now, if we find the standard deviation of these values, we get 3.0. Actually, this is the sample variance. Sample variance is 3.0. The sample variance for sample 2 is 2.0. And the sample variance for sample 3 is 2.0. And this is for dataset A. For dataset B, the sample variance is 3.0. The sample variance for 2 is 2.0, and the sample variance for sample 3 is 2.0. Okay, now for dataset A and dataset B, if we want to find the variance between samples, we would take the sample size and then multiply it by the sample variances of the sample means. Okay, so therefore we're going to take 4 and multiply that by 0.0833. So how do we get these numbers? We know that n is 4 from the sample size. Now we need to find the sample variances of all three of these means. So if I put in dataset A, there's mean 5.5, mean 6.0, and then there's mean 6.0. Okay, likewise, over here I'm going to do the same thing. I have 15.5 for dataset B, 6.0, and then 6.0. So if we take stat, go to summary stat, select columns, okay, let's select those two, and then let's take a look at the variance of those means. So the variance of those means is going to be the following. So if we take the variance of column A, you can see we get 0.833. So if we take the value of 4, which is the sample size, and multiply the variances of the sample means, we get 0.332. Okay, likewise, over here, we want to find the sample variances of these means. So we're going to take 4, and then the sample variance is 30.0833. And if we multiply it by that, then we get 120.3332. That represents the variances between samples. So if we want to find the variance within samples, we would take each of these sample variances and then divide by 3. So we would say 3.0 plus 2.0 plus 2.0 divided by 3 gives us 2.333. And then for dataset B, we would do the same thing. Take the sample variances and then divide it by 3, and then we get the same result. Okay, now in step 3, in order to find the F test statistic, we would take the variance between the samples, which we got, which is 0.3332, and then divide it by the variance within the samples, which is 2.3333, which should then give us the value of 0.1428. Now over here, if we take the sample variance for data set B that's between the samples, and then divide that by the variance within the samples, we get 120.3332 divided by 2.333 gives us 51.5721. You can see how much the F test statistic changes according to this sample. So you can see here that sample 1, when we added 10 to each of those, that F test statistic changed quite a bit. And then you can see here that the p-value is 0.8688 for data set A, which is a large. So we have a small F test statistic and a large p-value of 0.8688. Over here, we have a large F test statistic of 51.5721 with a small p-value of 0.0000118. Okay, now, if we want to find the variance between samples, what we just did above there, again, we're going to calculate the variances between samples by evaluating n times the sample variances of the means, where again, this represents the variance of the sample means and n is the size of each of the samples. That is, consider the sample means to be an ordinary set of values and calculate the variance. Now, from the central limit theorem, we know that the population standard deviation of the sample means is equal to the population standard deviation divided by the square root of n, can be solved for the population standard deviation to get the following. The square root of n is equal to the population standard deviation of the sample means, so that we can estimate the variance, the population variance, with n times the sample variance of the sample means. So for example, the sample means for data set A we found from 12.2 was 5.5, 6.0, 6.0, and 6.0, and these three values have a variance of 0.833, which we found on StatCrunch. So therefore, just like we did above, we have the variance between samples, which is 4 times the sample variance of the sample means, which gave us 0.3332. And again, we're just repeating the steps from what we did up here. Okay, and then we're going to find the variance within the samples. So we're going to estimate the variance within samples by calculating the variance, the sample variance, which is the pooled variance obtained by finding the mean of the sample variances. And the sample variances in table 12.2 that we found up here was 3.0, 2.0, and 2.0, and then we divided that by 3. So therefore, that's how we would find the variance within the samples. So getting that number, we get 2.3333. And therefore, in order to calculate the test statistic, we evaluate the F test statistic as follows. We would say that F is the variance between the samples, which was 0.3332, and the variance within the samples was 2.3333, which then gave us an F test statistic of 0.1428. So, understanding the effect of a mean on the F test statistic. Now, to really understand how the method of analysis variance works, consider dataset A and dataset B in the recent table and note the following. The 3 samples in dataset A are identical to the 3 samples in dataset B except for this. Each value in sample 1 of the dataset B is 10 more than the corresponding value in dataset A. Now, adding 10 to each of the data value in the first sample of dataset A has a significant effect on the test statistic, with F changing from 0.1428 to 51.5721. Now, adding 10 to each data value in the first sample of dataset A has a dramatic effect on the p-value, which changes from 0.8688, not significant, to 0.0000118, which is significant. Now, the 3 sample means in dataset A, which was 5.5, 6.0, 6.0, are very close. But the sample means in dataset B, 15.5, 6.0, 6.0, are not close. The 3 sample variances in dataset A are identical to those in dataset B, and the variance between the samples in dataset A is 0.3332, but for data set B it is 120.3332, indicating that the sample means in B are farther apart. Now the variance within the samples is 2.3333 in both data set A and data set B, because the variance within a sample isn't affected when we add a constant to every sample value. The change in the F test statistic in the p-value is attributable only to the change in sample mean 1. This illustrates the key point underlying the method of one-way analysis of variance. The F test statistic is very sensitive to sample means, even though it is obtained through two different estimates of common population variance. Now, in designing experiments, one way to reduce the effect of extraneous factors is to design experiment so that it has a completely randomized design in which each sample value is given the same chance of belonging to the different factor groups. Another way to reduce the effect of extraneous factors is to use a rigorously controlled design in which sample values are carefully chosen so that all factors have no variability. Informal methods for identifying which means are different. After conducting an analysis of variance test, we might conclude that there is sufficient evidence to reject the claim of equal population means, but we cannot conclude from ANOVA that any particular means are different from the others. Here are two informal methods for comparing means. Construct box plots of the different samples and examine any overlap to see if one or more of the box plots is very different from the others. Construct confidence interval estimates of the means for each of the different samples, then compare those confidence intervals to see if one or more of them does not overlap with the others. Formal methods of identifying which means are different. There are several formal procedures for identifying which means are different. Range tests allow us to identify subsets of means that are not significantly different from each other. Multiple comparison tests use pairs of means, but they make adjustments to overcome the problem of having a significance level that increases as the number of individual tests increases.